Hello again, my dear students, and welcome back to the second part of our Gaussian beam lectures. If you remember, in the first part, we have terminated with the feature associated with the Gaussian beam propagation of light related to the radial front phase, where light is propagating with radial front phase. In this case, we have concluded that a spherical matter is always recommended in order to fit with the radial front phase of the propagating light. And we have found that in our optical cavity, we can have two mirrors with two radii, R1 and R2, where R1 is equal to Z1, 1 plus Z node over Z1 all square, and R2 equals Z2, 1 plus Z node over Z2 all square. Now, what we are going to make in a very short manner in this very quick part is that we are going to try to solve these two equations, searching for an appropriate values for Z1 and Z2 at a given or at a certain condition. So let's start with the first condition. Okay, now I think it's better now to terminate it, to go to my whiteboard and start together solving these two equations. Okay, so let me pick up my pen and start. Let me first start with rewriting the equation. We have two radii, R1 equals to Z1, 1 plus Z node over Z1 whole square. And we have also R2, which is the second radius, equals to Z2, 1 plus Z node over Z2 whole square. So this is the two radii for the two spherical maps. What is the condition we are going to solve it? Let's see. So in the first case, let's assume that both radii are equal. So R1 equals R2. And this is simply occurs when if your cavities looks like that, then you will assume the source is centered in the middle. So this that equals 0. And then you have a distance of d over 2 in this side and a distance of d over 2 in this side, because if you remember, the distance between the two mirrors were d, the world distance. So that means that this is d, and you have d over 2 to the right and d over 2 to the left. And R1 is equals to R2 is equals to R. Accordingly, what you are going to do is that you will solve one equation saying that R equals 2. Now your propagation distance is d over 2, either to the right or to the left. So this d over 2, 1 plus z node over d over 2 all square. Let's solve this equation. So let me write it again. So it's R equal, R is the radius for the spherical mirror, d over 2, which is the propagation distance, 1 plus z node over d over 2 all square. So let's solve it for z. So it's now, let me do it like this. So 2 r over d equals 1 plus z node over d over 2 all square. Or we can make it that z node over d over 2 all square equals 2r over d minus 1. Now let's have the square root for both sides. Then z node over d over 2 equals to root 2r over d minus 1, or z node equals to root 2r over d minus 1 and still multiplied by d over 2. So again, why we are doing all these mathematical stuff? Z node is a distance. If you remember, Z node is equivalent to the distance at which you lose 50% of your intensity, if you remember from part number. So logically speaking, Z node should be a positive number, sorry, a real number, because it's a distance. Accordingly, this square root should be positive in order to make this a real function. Then the condition here should be 2r over d should be greater than 1. So this is the condition of resonance. To have a real Z node, then this condition should occur, and then you should design your cavity so that 2r over d should be greater than 1. And this is another condition. If you remember, we already have a set of conditions related to the condition for resonance in terms of the distance and the wavelength, which we use it in order to calculate what's called the free spectral range. We have the condition for gain, and we have the general condition for amplification inside the cavity. Now, whenever you are using an a spherical cavity, then you should add this condition to your condition. This conditions again correlate the the radius of curvature for the spherical mirror with the distance between the two mirrors. So this condition should happen. Okay, let's solve it for another condition. Now let's say that again R1 is equals to R2 is equals to R. And this R is equals to D. So you force R to be equals to D. And again, the light source is settled at D over 2. So you have a cavity here, and in the middle of the cavity, you are assuming that Z equals 0, your coordinates Z equals 0. So you have a distance of propagation D over 2 and a distance of propagation D over 2. Typically the same like the first. The only updated condition here that you set R equals to D. You set the radius of curvature to be equals to the distance between the two mirrors. So what will happen? Let's first write the equation. R, which is the reflectance, equals to Z times 1 plus Z node over Z whole square. Okay, then R will be replaced by D. Z will be replaced by D over 2, the distance of propagation. 1 plus Z node over D over 2 whole square. This D will be cancelled with D, then you have 2 here, 2 equal. Then we have 1 plus Z node over D over 2 all square. Accordingly, you can put this here. So Z node over D over 2 all square is equals to 1. And then you can find that in this case, you have an exact value of Z node equals to D over 2. Herein, as you can see, you have of course, this square root will result with a positive or negative, but of course, whenever it's a distance, it should be positive. Then we have only one solution where Z node equals to D over 2. This is simply the second condition. So here you have an exact value. So if you settle or if you design the radius of curvature to be equal to the distance between the two mirrors, then what will happen simply is that by reaching the mirror, which is the distance D over 2, you will lose 50% of your light intensity, which is again the definition for the distance Z. Okay, so now let me return back to my presentation slides again to show you this description. Okay, so let me share screen. I believe now you can see it. Okay, so perfect. So let's do it one more time. These are the two conditions, the two equations for the two radii, R1 and R2. The first condition is when R1 equals R2 equals to R, the center, the light source or the center of the Z is considered as D over 2. Then you have this equation, and then you have this condition, which is 2R over D is greater than 1. However, whenever the condition is added to have R equals to D, we will have an exact Z node, which is equals to D over 2. These are the two conditions related to two different ways. If you access the manuscript, the lecture script, I mean, you will find two more sections. In the first section, we are considering what if the optical cavity, in addition to the propagation coefficient, K, and in addition to the gaining factor, gamma, if you remember lecture 5, you have also an attenuation coefficient alpha. Similarly to the attenuation coefficient you have seen before in your microwave classes and in electromagnetism classes, e power minus alpha z. Then, how should the gain coefficient looks like? So this is for your knowledge. It should be a part of the course, by the way, but however, due to the limited time of the course this year, we have skipped this, so you can access it for your knowledge, which is a general equation for an optical cavity. And you will find also what's called the ABCD matrix, which is a way where you can use in order to express any optical device, maybe this mirror, this spherical mirror, or whatever, in a form of 4 matrix coefficient. It is something, maybe most likely it's something like the S parameter in the microwave system. Not that much, but somehow the same procedure. So you can easily manage any optical device in the terms of these ABCD, and you can cascade systems by easily multiplying these matrices together in a matrix multiplication form, and then you can get the equivalent of the system. So this also should be a part of the course. However, due to the shrinked time frame of this course this semester to be only a 10 weeks course instead of being a 12-week course, we also have skipped this part, not to be a part of your MSc exam. Accordingly, my dear students, after finalizing the two conditions related to the propagation or the radius of curvature of the spherical mirror in a spherical cavity, with respect to D, which is the distance between the two mirror, and Z node, which is the distance for propagation at which the light intensity reached its half, then this will be considered at the end of our course. Now it's 10 weeks course, a lot of mathematics, a lot of concepts, a lot of optics, of course. I hope that you have enjoyed this course. Maybe this is considered somehow an interesting course for some of you, and maybe it's not that much interesting for others, but in all ways, I have to thank you for your concentration, for your dedication, for your efforts, and I have to wish you all the best of luck in your coming unseen exams. Maybe we will have an extra solving session concerning the unseen exam, but my advice is please listen to our recorded lectures very well. Please go to the tutorial problems. Please access more problems using our references, either the optical communication reference for the first 2 chapters or Verdine for laser electronics in the last 4 chapters. And by the end of the day, as this your final semester course, what I have to do is not only to wish you luck in your unseen exam, but also to wish you luck in your next near future career as a respected and valuable engineer to the market. Thank you very much. Wish you all of luck and see you later on after your graduation as a very powerful, successful alumni. Thank you very much and see you later on.